but आपने 7:30 आउटगोइंग थे, आपने आउटले 7:30 आगे एक बार फोन कराने होना चाहिए 7 ऐसा कैसे कर लो बेटा, ठीक है Okay, good evening all of you. In today's meeting we are going to continue with wave optics. In wave optics, what we are going to do is that we are going to begin with Higgins principle. So there was a scientist known as Higgins. He made a statement that whenever light propagates, it propagates in the form of waves. So that was very much the opposite of what people like Sir Isaac Newton said. So people like Sir Isaac Newton said that light is propagating in the form of particles, but Higgins confirmed that light is actually propagating in the form of a wave. So according to Higgins, what happens is that because light propagates in the form of a wave, at any point of time during the propagation, the various points which are in the same phase, if you connect all of them, then the you will be tracing something called a wavefront. So what is a wavefront? It is obtained by tracing you know the join of all the points which are in the same phase. So you have S1, S2, S3, and you are just joining all of them like this. So this shape is called a wavefront. So wavefront is the trace of all the points which are in the same phase. Now, according to Higgins principle, you are standing on a wavefront and you want to know the position of this wavefront at a later time. So you have to remember one very important thing is that the propagation of light itself will always be perpendicular to the wavefront. So that means the light itself will propagate, like this, like this. So the propagation of light will always be normal to the wavefront. And I think if you go back to the concept of transverse waves, you'll find that this makes sense. We know that in a transverse wave, the propagation and the disturbance are perpendicular to each other. So you are interested in finding out the new position of the wavefront, let us say after a certain time interval t, you want to find the new position of the wavefront. So what you have to do is keeping S1 as center, you draw one arc, okay, and you want to know the position of this wavefront after a time t. So keeping S1 as center and radius v into t, you draw one arc, right? So keeping your compass at S1 and radius vt, you draw one arc. This arc is called a wavelet. So this arc is called a wavelet. Similarly, taking S2 as center, you draw another arc. So this is also called a wavelet, right? Wavelet is also called secondary wavefront. So wavelet is also called secondary wavefront. The primary wavefront is this, and wavelet is also called secondary wavefront. So what you have to do, once again I'm saying, this is the position of the wavefront at a particular instant of time, and taking different points on this wavefront as center, if you draw these arcs, so each of these arcs is called a wavelet. Okay, each of these arcs is called a wavelet. And then you must draw the geometrical envelope of these wavelets. So the geometrical envelope of these wavelets, okay, this is the new wavefront. So the geometrical envelope of these wavelets is the new position of the wavefront. So once again, you have a light wave, it is propagating, you have drawn one wavefront, right, at a certain point of time. On the wavefront you have taken certain points like S1, S2, S3. So each of these S1, S2, S3, it becomes the source for the next wavefront. And how do you find the next wavefront? With each of these points S1, S2, S3 as center and radius equal to velocity of light into time. So velocity of light, well, if it is vacuum, it is 3 into 10 to the power 8. If it is not vacuum, some other medium, it will be a different value. So velocity of light into time is a radius. You draw the wavelet, draw the wavelet, draw the wavelet, right? And then you draw the geometrical envelope of all these wavelets. So the geometrical envelope of all these wavelets is the new wavefront. So this is called Higgins principle, right? So According to uh, Higgins principle, um, whenever a wavefront, whenever light is propagating, so let me just say summarily what is Higgins principle. Whenever light is propagating, it is always going to propagate in the form of waves, right? And in any wave, there will be particles in various phases of disturbance. If you connect all the points which are in the same phase of disturbance, then the join of all those points is the wavefront. So I have joined all the points which are in the same phase of disturbance, so I am getting a wavefront. Then on the wavefront, if I take different points like S1, S2, S3, then each of these will become the source of a secondary wavefront which is called a wavelet. So each of these S1, S2, S3 becomes a source of a wavelet. And how do you construct the wavelet? You take S1 or S2 or S3 as center and draw an arc whose radius is equal to velocity into time. So what you will get is a wavelet. So this one, this one, this one, these three are all wavelets. After constructing the wavelets, you will have to draw the geometrical envelope of all the wavelets, and the geometrical envelope of all the wavelets will be the new wavefront. So this entire technique and this concept involved is known as Higgins principle, right? So in Higgins principle, what are the things that you need to know? Like I said, that the wave itself will be perpendicular to the wavefront. The propagation of the wave, like these arrows are showing the propagation of the wave, that will be perpendicular to the wavefront, right? That is number one. Number two, you will notice that the wavefronts which I have drawn, they are appearing to be spherical. So spherical wavefront will always come from a point source, right? If you have a point source, then light will emanate in all directions, and therefore the wavefronts will be spherical. So spherical wavefront will happen whenever there is a point source. So this is the total concept of Higgins principle. Now, what is the use of Higgins principle? You will be surprised to know that the two most iconic laws of light, which goes way back to the lower classes, the laws of reflection and the laws of refraction, they are actually derived from Higgins principle, right? So what we will do now is one by one we will look at the derivation of each of those laws. First, let us look at the derivation of laws of reflection. Okay, now listen to this carefully. A, B, this is a mirror. So basically you're talking about laws of reflection, so there has to be a reflecting surface. So AC is the mirror, excuse me. AC is the mirror, so it is the reflecting surface. Now there is a incident wavefront AB. AB is the incident wavefront, and A is already in contact with the mirror. A is already in contact with the mirror, and B will be going to meet the mirror after some time. So let us say that B will meet the mirror after a time t. So let us say that B is going to meet the mirror after a time t. So BC will be V into t. V is the speed of light. So A has already reached the mirror. B will reach the mirror after a time t. So BC will be V into t. Now what we will do is we will start using Higgins construction, Higgins principle. So first thing we will say is that BC is V into T. So during the time that B reaches C, obviously A would have left the mirror and gone back. That's what happens in reflection. So this V into T, taking V into T as the radius, taking this V into T as the radius and A as center, you draw your wavelet, right? You draw your wavelet. You know that in order to get the new position of the wavefront, it is compulsory to draw the wavelet. So taking A as the center and VD as the radius, you draw your wavelet. So taking A as center and VT as radius, you draw the wavelet. Now, but then we have got one wavelet. Now what about the new wavefront? How do we get that? So remember what I told you, that the propagation of light will always be perpendicular to the wavefront. So this wavelet which I have drawn, essentially it is spherical. So if I draw this line, that is a radius, and this is going to be the reflected ray, right? The way I have shown one arrow, just like BC is the incident ray. So this thing is the reflected ray, right? And the wavefront has to be perpendicular to that. So what is perpendicular to radius? Tangent. So from the point C, you draw tangent to this wavelength. Something like the way you would draw a tangent to a circle from an external point, something like that. So from C, you draw a tangent to this wavelength. So this tangent will become the new wavefront. So AB is the incident wavefront and CD is the reflected wavefront. So you know that this angle is 90. Similarly, you know that this angle is 90, right? The reason is that only that the radius and the propagation direction and the wavefront are perpendicular. That is the reason. Now you consider triangle ABC and triangle ADC. You consider these two triangles, ABC and ADC. So number one, AD is equal to BC equal to VT, right? Number one, AD is equal to BC equal to VT. That is number one. Number two, AC is common. Number two is AC is common. Number three, angle ADC and ABC both are 90 degree. So in triangle ABC and ADC, AD and BC both are equal to V into T. so they both are equal. Secondly, AC is common. Thirdly, angle ADC and angle ABC both are 90 degree. So that means triangle ABC is congruent to ADC. ABC is congruent to ADC. So since ABC is congruent to ADC, so we can say that angle BCA equal to angle DAC. Now I have drawn two dotted lines. This is a normal at C, this is a normal at A. So this angle over here, this is the angle of incidence I. D and AB are in the same plane. So AD and BC are in the same plane. And also the two normals, each of the two normals is in the same plane as that particular ray. Like this normal is in the same plane as this ray, this normal in the same plane as this ray. So that means the incident ray, reflected ray and normal all lie on the same plane. That is the proof of the second law of reflection. So you can see how Higgins principle has helped us to prove both the laws of reflection. So the first law, angle of incidence equal to angle of reflection, done. The second law, the incident ray, reflected ray and normal, all three of them lie on the same plane. So this entire discussion is the proof of the law of reflection using Higgins principle.
So, ahí está el foto.
Okay, so now we move on to the next part of Higgins principle, that is the proof of laws of refraction. So suppose AB is the incident wavefront. Okay, suppose AB is the incident wavefront and this is the boundary separating the two mediums. Okay, this line is the boundary separating the two mediums and AB is the incident wavefront. So at the time of consideration, A has already hit the boundary of the two mediums. A is already on the boundary. B is about to reach the boundary. It has not yet reached. So B will reach the boundary of the two mediums after a time t. So that means from B to the boundary, the distance will be the speed of sound into t, like v1 into t. So BC will be v1 into t. Now what you do is, with A as center and radius V2 into T, you draw a wavelet. But the wavelet, you have to draw it in the other medium, the medium into which the ray is getting transmitted. So with A as center, you draw a wavelet, but this time the radius will be V2 into T, because this medium, the velocity of sound is V2. So with A as center, you draw a wavelet of radius V2 into T. Then you know the concept that propagation is perpendicular to the wavelet or the wavefront. So the ray is propagating like this is the incident ray, this is the refracted ray. This is obviously hand drawn, so not a very accurate diagram. Usually the refracted ray will either bend towards the normal or away from the normal. So here that is not very apparent. This is a hand drawn diagram. Now the refracted wavefront, how do we get it? So from the point C, you draw a tangent to this wavelet. So suppose the tangent is CD. So from C, you draw a tangent to the wavelet. Suppose the tangent is CD. Then automatically CD will become the refracted wavefront. So AB is the incident wavefront, CD is the refracted wavefront. Angle of incidence is I, angle of refraction is R, and by basic geometry we have established that this angle will also be I, because this is I, so this is 90 minus I, this one, and therefore this is I. This is R, so this is 90 minus R, so therefore this is R. And obviously there are two right angle triangles, one is ABC and one is ADC. Now in the right angle triangle ABC, suppose I want to do sin I, so it will be BC by AC, so V1T by AC. In the triangle ADC, suppose I want to do sin R, so AD by AC, so V2T by AC. So sin I by sin R is equal to V1 by V2. So sin I by sin R is V1 by V2, right? So sin I is V1T by AC, sin R is V2T by AC. So sin I by sin R is V1 by V2. Now V1 is the speed of sound in the first medium, V2 is the speed of sound in the second medium. So for a particular temperature, physical conditions, if they are the same, the speed of sound usually will not change. Like suppose if there is a, not speed of sound, speed of light. So if the speed of light usually will not change for that particular medium, okay, unless there is a drastic alteration in the physical conditions. So V1 by V2 is a constant. This is known as refractive index. So this ratio V1 by V2 is called refractive index of medium 2 with respect to medium 1. Okay, this V1 by V2 ratio is called refractive index of medium 2 with respect to medium 1. So V1 by V2 is equal to sin I by sin R is refractive index of medium 2 with respect to medium 1. This is the definition of refractive index, and therefore you understand that V1 by V2 will be a constant for this pair of medium. Sin I and sin R, they will have changing values. If I and R keeps changing, sin I and sin R will keep changing, but the ratio sin I by sin R will be a constant equal to V1 by V2. So this is the entire concept of refractive index. Okay, now laws of refraction. There are two laws, and you know that they are collectively called Snell's laws. So the first Snell's law is that the refractive index of medium 2 with respect to medium 1, which is V1 by V2, is sin I by sin R. This is in fact Snell's law, right? The law of refraction. This is Snell's law. So we have already proved Snell's law. By way of this derivation, we have already proved it. The second Snell's law, this is the incident ray, okay, this is the incident ray, it will be in the same plane as the wavefront AB. Wavefront AB and wavefront CD will be in the same plane. Refracted ray will be in the same plane as wavefront CD. And normal is common to both and in the same plane. So incident ray, refracted ray, and normal lie on the same plane. So that is the second law of refraction. So both the laws of refraction, Snell's law, sin I by sin R, V1 by V2 is refractive index of 2 with respect to 1. That is also proved. And incident ray, refracted ray, and normal lie on the same plane. That has also been established. So these are the two laws of refraction. So this is the discussion of Higgins principle and how it helps us to prove the laws of refraction and laws of reflection, which we did before this. Okay, the next topic is interference in thin films. Okay, the next topic we are going to do is interference in thin films. Let me just give you a quick introduction to this topic. What is this topic, interference in thin films? If you see, sometimes in our city when there is extreme rain and the roads are flooded and the vehicles are trying to maneuver through the waterlogged roads, you will find that there is a oil spill out of the vehicle, and when you look at the spilled oil from various angles, you will see very different pattern of colors. The same oil spill, the way you look at it, the point of view rather, will determine the pattern that you will be able to see. So this is due to interference in thin films. So basically this small d is a thin film, okay, and this is the incident ray that is entering the thin film. Now this incident ray, after it strikes the thin film, it can either reflect or it can get transmitted and go inside. After getting transmitted, so when it reaches the opposite end, it can transmit and come outside, or it can reflect and go back. After reaching here, either it can transmit or reflect and go in. And in this way, you can have always two possibilities, resulting in a bunch of rays which are called the reflected rays, which are meeting at P dash, and you will have a bunch of rays which are called the transmitted rays, which are meeting at P. And so we are going to discuss the interference concept related to this. So so for the refracted rays, so suppose this point is A, this is B, this is C, this is D, this is E, this is F. So the path difference between BP and DP, the path difference between BP and DP is equal to BC plus CD. And remember, this is a thin film, so BC plus CD, it will be equal to 2D, right? So this is the path difference, but path difference inside the thin film, and suppose the refractive index of the thin film is mu. So the optical path, last class we had discussed this topic, optical path. So the optical path will be 2D into mu. So the optical path will be 2 mu d, right? So this optical path is what we called the actual path difference, right? Optically speaking, delta x. And you are aware that the phase difference is equal to 2 pi by lambda into delta x. Now the thing is that if delta x is n lambda, that means delta is 2n pi, right? So if 2 mu d is n lambda, that is delta is 2n pi. In that case, the refracted waves interfere constructively. Okay, so I'm saying it again. The optical path is 2 mu d, and that is equal to delta x, and if that is suppose n lambda, and delta, that is the phase difference, is 2 pi by lambda into delta x, that is 2n pi. So if these two conditions, they are both the same actually, that means the refracted waves, like these waves which are coming out due to refraction, they will অফ করি, আপনার অসুবিধা হবে? সুবিধা অফ করে দেখবো পরিষ্কার হয়ে যাচ্ছে কি না। আমি শুভজিৎ অফ করে দেখছি, আপনি আমাকে বলুন যে ঠিক আছে। শুভজিৎ অফ করছি, এক্ষুনি করছি। Okay, what I have done is that I am not closing the stream. What I have done is that I have altered the Wi-Fi settings. Okay, the Wi-Fi which is yeah, actually there does seem to be a problem with the there is probably there is some problem with the upload speed. I think there is some problem. I'm not able to gauge how much it is right now. There might be, because the video resolution and all has been set to a very high level. There might be a problem in the upload speed. I don't think I will be able to check it now. There might be an issue. See, if it is continuously blurry, then I'll have to close the stream and start it again. But if it is blurry in patches, I think it could be because of the variable upload speed. Okay, that shouldn't happen, but that is the probable cause. So the refracted waves interfere constructively. So B to P, D to P, they will all interfere constructively if the path difference is n lambda or phase difference is 2n pi. Okay, now listen, all of you. The thing is that for reflected rays AP dash and BP dash, the path difference is AB plus BC, which is approximately equal to 2D. So the optical path will be 2D into mu. So 2D into mu, that means this will be the condition for destructive interference. Okay, destructive interference. 2 mu d equal to n lambda. This will be the condition for destructive interference. Now, why is that the case? Why is it like that? It is simply because of conservation of energy. When something like in case of mechanical energy, when potential energy is maximum, kinetic energy is minimum, but the total mechanical energy is constant. So here part of the light energy is going for the transmitted wave, part of the light energy is going in the reflected wave, but the overall value has to be the same. So you cannot have maximum intensity of refracted and reflected both. Refracted and reflected, you cannot have maximum intensity. That means that when the refraction is maxima, the reflection will be minima. So that means delta x equal to 2 mu d equal to n lambda will be the condition for destructive interference. So delta x is 2 mu d is n plus half lambda. This is the condition for constructive interference, right? So delta x is 2 mu d is n lambda is destructive. So in case of refraction, it was constructive. And delta x 2 mu d is n plus half lambda. That will be for refraction it was destructive, and for reflection it will be constructive. So the idea is that you cannot have maximum intensity of both refracted wave and reflected wave. So the interference will be such that if refraction is maxima, then reflection has to be minima. Both cannot be simultaneously maxima, or that would mean excess energy. Both cannot be simultaneously minima, that would mean loss of energy. So this is the concept interference in thin films. Okay, now one important thing I wanted to say to all of you, that in this chapter light waves, actually we are left with two topics. One is single slit diffraction, and that is number one, and number two is polarization. So we are left with two topics in this chapter. Now the issue is that for doing these two topics, single slit diffraction and polarization, for doing these two topics it will take about 1 hour, and both the topics will be over, single slit diffraction as well as polarization. So we can complete both the topics in exactly 1 hour. So keeping that in mind, I feel it will be perhaps a better thing if we complete both the topics the next day, and if we do that, then we just have modern physics part of the syllabus left, right? So I think that would be a more sensible thing to do, rather than try to cram the whole of the chapter in one single meeting. So my suggestion is that let us quit for today, and next day we will do polarization and single slit diffraction. We will do both the topics, and that way we will be able to complete light waves. So after the next class, we will be just left with modern physics, which I think is a total of 3 chapters: atoms and nuclei, dual nature of matter and radiation, and semiconductors. Total there are 3 chapters in modern physics, right? So that's it. I think we'll conclude the meeting for today. We will do polarization and single slit diffraction in the next session. Thanks a lot all of you. I'll conclude the meeting. Thank you.